So before we get started, we're going to be talking about conservation of energy, which pretty much states that energy cannot be created nor destroyed. And inside the system of the spring, energy is going to be conserved when we put it inside it. So when someone stretches the string out, then as it's oscillating back and forth, it is going to be maintain the energy that it has for each point on the spring. So we could effectively say for right here, first frame of reference, E of 1 is equal to E of 2. And as a result of this, we can create this table right here where each one of the columns is equal to one another. And what this allows us to do is create various system of equations that allow us to find certain values within our equation, most definitely the amplitude and the speed at one particular point. So we're going to go ahead and get started and use this method to find the amplitude. Today, we are going to be finding the amplitude. In order to find amplitude, we are going to be working a system of equations based off the energy of point 1 and point A, where A is the amplitude point, and 1 is the point of which D is equal to 5 centimeters. Now what we can do is we can plug this right over here into our energy grid, and what we can input is a KE of 0 for point of amplitude, because we know the velocity at the amplitude point is equal to 0, and UG would be 1/2 times K of 2.5 times the D squared. The KE at position 1 would be 0.5 times the mass, which is 0.1, times the velocity, which is 0.2 squared. The spring energy at point 1 would be 1/2 times K of 2.5 times the D of 0.05 squared. And what we can do is we can put that into our long equation. And what we're going to go ahead is we're going to go ahead and move this all over to one side. So that's going to give us an equation of D is equal to, and when we plug this into our calculators, we are going to get a D of 0.064, or in other words, 6.4 centimeters. And because this is the amplitude we're referring to, it'd be plus and minus, because it can go to the right side and the left. So the next part of the question is that we're going to be finding the maximum acceleration. Maximum acceleration is going to be at this point right here. The amplitude, because we know that at the furthest away from the equilibrium point is where the most amount of force is going to be applied onto the block. So what we're going to do is we're going to use we're going to find a second derivative of an equation for x, the distance. Now that is the phase constant, and in this equation that's going to equal 0. But because the whole cosine is going to be equal to 0 later when we discuss how t is 0 as well, we will not discuss about the phase constant. Now in order to find the derivative, we're going to go ahead and transfer this into velocity by taking the derivative of all of it. And we're going to go ahead and take the derivative again, which is going to give us our acceleration. As I mentioned earlier, t and phi both equal 0, so that's going to allow us to extract that for cosine of 0, which equals 1. So our final maximum acceleration at this point, the amplitude, is equal to omega squared times the amplitude. Now, omega squared, we're going to swap that out, because we know that omega is equal to the square root of the spring constant K divided by m, where m is the mass of the object. And we're going to go ahead and execute that now into an equation that we can simply plug in values to and find our answer. And once we do, we're going to find that the acceleration is equal to 1.6 meters divided by seconds squared. So we're going to be hitting the last part of the question, which is finding the speed at d is equal to 3 centimeters. Now I've already drawn it right here. Essentially, like the first part, we're going to be setting up another frame of reference where it is equal to 2. And we're going to be comparing it to the first frame of reference, of which we've already calculated the values of, to frame of reference 1. Now, in order to find the kinetic energy, we do not know that yet because V is an unknown value. So we're going to go ahead and mark it with a variable. And we're going to times it by the mass of 0.1 times 1/2 or 0.5. We are also going to extract the spring's kinetic or potential energy of 0.5 or 1/2 times the spring constant of 2.5 times d or 3 centimeters or 0.03 meters squared. Now, each one of our equations has 0.5 inside it. So what we can do is remove 0.5 from the whole system of equations because each one of these has it inside their equation. And we're going to go ahead and transfer this all to one side. Once you calculate the value of V, you'll get 0.28 meters a second is equal to V, and that is how you do the problem.